integral x plus 1 divided by divided by x cubed plus 8x squared plus 16x dx. All right, so um, we're going to go ahead and use decomposition once again, all right, just because numerator has a degree less than the denominator. If we go through and factor this, the first time, we're going to need two factorizations. So we're going to get x plus 1. We're going to factor out a GCF of x. That's going to leave us with x squared plus 8x plus 16. Second factorization is we can write this as x plus 1 over x plus 4x plus 4. And then finally, we could rewrite this as x plus 1 over x quantity x plus 4 squared. All right, and what does this end up being? Well, what it looks like is that we're going to have one distinct linear factor and then a repeated linear factor twice. And so if I was to go through and do the decomposition, at least set it up, that's going to be a over x, so that's not too bad, and then b over x plus 4, and then unfortunately, we get this c over x plus 4 squared. All right, now I know x plus 4 squared would FOIL into a quadratic, but internally it's a linear factor, which is why we don't need cx plus d. We're going to multiply through by the common denominator, and it's going to leave us with x plus 1 a x plus 4 squared bx x plus 4 cx. Right. Now, at this point, what we could do is we could either create a system or we could go through and use the nice number method. I think what I'm going to do is I'm going to use the nice number method, and I'm going to start by letting x equal 0, okay? Because what that'll do is that'll take care of the b and the c, all right? And so if we plug in x equals 0, we get 1 equals a, 0 plus 4 squared, and then b cancels out and c cancels out. So realistically, 1/16 is equal to a. Another nice number that I can use, in fact, the only other nice number I can use is going to be x equals -4. All right, and that's going to wipe out the a's and the b's, but unfortunately, we're not going to be able to solve for everything yet. Okay, so if we substitute -4 back in, that's going to give us -3. -4 plus 4 squared is 0. B times -4 times 0 is 0. And we get -4c. And we get 3/4 equals c. All right, so not so bad so far. All right, however, unfortunately, we're going to have to substitute back in, and we're going to have to pick one last nice number to be able to kind of work with this. All right, so now when we substitute for a and b, we're going to wind up with x plus 1 is equal to 1/16. All right, we really don't like that. X plus 4 squared. We still have bx, x plus 4, and then we're going to have 3/4 x for c. All right, so a couple nice numbers that we could think of aside from 0 and then -4. What about something like 8 or -3? All right, and the reason I say 8 is because you might be able to get rid of some of these denominators, okay, and make it work out nicely. If I use -3, then that would make this a 1, this a 1, all right, and then I'd only have like a little bit to work with. So what I'm going to do is I'm going to pick -3, all right, just because, yeah, that's what I feel like. You could use whatever numbers you want, they'll work, all right? And so if I use -3, we get -2, 1/16. When I plug in -3 here, I get a 1 squared. So it's really 1/16 times 1. All right, and that doesn't really matter to us, right? And then over here, we're going to have b times -3 times 1. So it's -3b. And then finally, over here, I'm going to multiply by -3, and that's going to give us the -9/4. Right? Now we just have a basic linear equation to solve. I'm going to multiply everything through by 16. So I'm going to get -32 equals 1 minus 48b and then minus, if I multiply through by 16, that's going to be 144 over 4, which is 36. All right. I know it looks ugly, but it could be a lot worse. This becomes negative 35. Add 35 to both sides. It's going to be 3, negative 48b. And so I believe we should get negative 1/16 for b if I didn't make any sign errors or anything like that. Okay. Probably should have checked this before I did the problem. All right. So now we can go through and go back up here, substitute for a, b, and c. All right, and then just integrate. All right, so we're going to end up with the integral of 1/16 over x dx. We know that b is a negative 1/16, and that was going to be divided by x plus 4, and then we get 3/4 x plus 4 squared. And finally, we have integral of 3/4 x plus 4 square dx. All right. So 2 of these are easy to integrate. The first 2 are just going to end up being your natural logs. Okay. Unfortunately, the last one is going to require a u substitution. All right. So u is going to be equal to x plus 4. Du is dx. And I'm just going to operate on that one. Okay. So I'm not going to worry about any of the other ones for right now. So that's going to lead me to the integral. And this is just coming over here in terms of u, 3/4 integral of du over u square by substitution. I'm just going to turn this into a u to the minus 2. All right. And now we can integrate all of the terms. All right. So integrating this and this, that's going to be 1/16 natural log absolute x minus 1/16 natural log x plus 4. Right. And then finally, when we integrate this guy, it's going to be negative 3/4 u to the minus 1 plus c. We're going to back substitute for u. We're going to simplify these logarithms. All right. And one possible answer that we can get after we do all the simplification is we're going to end up with the natural log of the 16th root of x over x plus 4. All right. So again, 1/16, 1/16, 16th root, positive on top, negative on bottom, minus 3/4. And since it's u to minus 1, it's going to go to the bottom. U is x plus 4, and then plus c. All right, so this is probably the solution that a computer algebra system might give you, or if you were to try to plug it into MyMathLab or something, that it might want you to try to write this. All right, so 2 more examples. We're getting close to being done this section. Making sure that I give you plenty of examples just because this section is relatively tedious because of the partial fractions coupled with the integration techniques.